This is an overview of two ways to test for linear associations among variables. First, I will cover correlation, which quantitatively evaluates the linear relationship between two variables. Next, I will review regression, which similarly evaluates the linear relationship between an outcome, or dependent variable, and one or more theoretical predictors, or independent variables. We prefer regression when we have a good idea of causality and generally more data. Note that linearity is an important assumption of these techniques. That is, the graphical relationship between the outcome and the group of predictors is a straight line. One reliable way to meet the linearity assumption is to transform variables toward normal if necessary. A correlation coefficient is a numerical measure of a statistical relationship between two variables. The correlation coefficient is the most basic way to empirically determine the relationship between two variables. In calculating the correlation coefficient, neither of the two input variables can be purely categorical. There must be a hierarchy of values in the measure. As with interval and ratio data, there are two basic types in common use. First, Pearson's R is mainly used for two variables characterized by asymptotic normality or near normal distributions. Second, for variables departing from normality, the Spearman's rank is preferred. Thus, Pearson's R is considered a parametric option and Spearman's rho is considered a non-parametric option for assessing the relationship between two variables. In either case, the correlation coefficient is interpreted the same. Both statistics range from -1 to 1, with 0 implying no relationship between the variables. A perfect -1 correlation coefficient means the two variables are perfectly negatively related, while a value of 1 represents a perfect positive relationship. This graphic shows perfectly negative, 0, and perfectly positive correlated data. Here is perfect negative correlation, perfect positive, and no correlation whatsoever. It also shows other positive and negative value scenarios. Linear regression is named such because it assumes and is interpreted as there being a linear relationship between a dependent variable and one or more independent variables. As you can see here, linear regression models include additional information that the correlation coefficients do not. It shows the nature of the relationship. In this case, it would be a positive relationship, but it also shows a y-intercept. This is the x-axis and this is the y-axis. And you can see that where the x values are 0, the response variable or dependent variable is at 5. This value is called the constant in a regression equation. The slope here is called the beta coefficient in a regression equation. When a linear regression contains multiple independent variables, there will be multiple beta coefficients, and this graph will get a lot more complicated. It will be as complicated as there are number of independent variables. Later in this presentation, I will show you a depiction of this type of scatter plot with multiple independent variables. It's important to talk about the assumptions of linear regression. The first assumption is normality. Your book talks about the importance of a normal distribution as a characteristic of the dependent variable. Linear regression is most appropriate when the data is asymptotically normal. Again, that means near normality. If the data is not, researchers should consider other classes of regression, such as ordinal, partial least squares, nonlinear, or, as will be explained later, binary logistic regression. Thus, the distribution of variables will influence the regression technique used. As the name implies, linear regression also assumes linearity between the x and y variables. You can see in this diagram on the left, that implies a positive linear relationship. The next one is a negative linear relationship. And the graph on the far right shows a nonlinear relationship. In the case of a nonlinear relationship, it would be appropriate to change the distribution of one or two variables through transformation in order for the regression equation to adhere to this assumption. Another linear regression assumption is independence of values. This mainly comes into play when there is time-ordered data. What we're trying to do is make sure that time shouldn't be a variable included in the analysis as an independent variable. When you chart values over time, you don't want a variable to be partially determined by time. So in this top graphic, you can see that time does not affect the value. In the middle graphic, you can see that time does affect the value. In that case, the values are dependent on time. Time can have a positive or negative association with the variable being evaluated. Another assumption is multicollinearity. This is a concern when you have multiple independent variables or variables you're trying to use to predict the dependent variable. We want the independent variables to be, as their name implies, truly independent. We don't want them to be correlated with one another. That is because they will explain the same phenomenon when they are, indeed, empirically correlated with one another. We want unique independent variables that explain different concepts. That will make our regression equation more reliable over subsequent samples. Another linear regression assumption is homoscedasticity. As you can see from this graphic on the left, the variance of values is much tighter over this range as values are smaller on the x-axis than when x grows. When x gets larger, the variation increases. We don't like that in linear regression because that means that values are interpreted differently on the left-hand side of the timeline than the right-hand side because variances change. Same with this middle diagram. You can see that variance changes over different values of x, so we can't interpret along the x number line the same. Ideal is what we call homoscedasticity on the right-hand side, where we have consistent variance on the regression line. I'm going to give you a brief example of simple linear regression. I showed you this diagram earlier, and this is a depiction of simple linear regression, which means you have one x or independent variable, and with that you're trying to explain a y or response or dependent variable. Simple linear regression is similar to the correlation coefficient in that it evaluates the linear relationship between two variables. However, simple linear regression designates one variable as the dependent variable, i.e. the outcome or response variable, also designated as y, and the other as the independent variable, also termed the predictor and designated as the letter x. Shown here is the output of regressing green vegetable consumption as the predictor variable on BMI or body mass index as the dependent variable. The model fit can be ascertained from the model summary table. This table reveals the model R-squared value, which ranges from 0 to 1 and depicts the level of association between the two variables. As shown, the test did not produce evidence that green vegetable consumption explains BMI. As you can see, the R-squared value is 0.000, which means the two variables are completely uncorrelated. The ANOVA table shows the same thing with a significance value of 0.915 indicating no association. If there was a significant relationship found, the output also produces a highly informative regression equation. Here we can see that the unstandardized beta value for the constant, also known as the y-intercept value on a scatter plot, is 27.492. This means that when the independent variable, green vegetable consumption in this case, is 0, the BMI averages 27.492 in the sample. The table also shows that the unstandardized beta coefficient for the independent variable, again green vegetable consumption, is 0.003. This is shown here. This means the relationship is positive. However, the significance value of 0.915, shown here, indicates that green vegetable consumption does not associate well with BMI. Thus, the model indicates there is no significant relationship between the two variables, a potentially insightful scientific finding. However, the researcher's job may be incomplete, as the possibility of variable transformation remains an option in subsequent reformulations of the model. Another option is to add independent variables that theoretically should also associate well with BMI. Multiple linear regression is an extension of simple linear regression in which more than one independent or predictor variables are entered into the analysis. Interpretations of multiple regression findings are much the same as with simple linear regression. However, as the name implies, multiple linear regression equations will be represented by multiple beta coefficients and significance values, one for each independent variable. A single R-squared value will be reported and interpreted the same as with simple linear regression. Multiple linear regression is considered more powerful because more variables are leveraged to explain the dependent variable. Also, all predictors may be tested simultaneously, which means each beta coefficient can be interpreted in the presence of every other model-independent variable. Multiple linear regression is appropriate when the variables are continuous, measured at the interval or ratio level, or using a binary independent variable. You can see from this diagram the multidimensional nature of multiple linear regression. I hope you learned from this overview of correlation and regression. Thank you.